Hello everyone, my name is Vaishnavi and I'm pursuing my second year of engineering in cybersecurity from Sri Venkateshwara College of Engineering. Today, let's start with the topic K-map, its advantages and disadvantages. Karnaugh-Maps, a powerful tool for Boolean expression simplification. Karnaugh-Maps, that is K-maps, are a visual method used to simplify Boolean expressions, representing them in a structured grid format. This approach offers a streamlined way to identify and combine terms, leading to minimized logic circuits. What is a K-map? A K-map is a graphical representation of Boolean expressions truth table. Each cell in the map corresponds to a unique combination of input variables. Coming to the visual representation, it visually organizes truth table information, making it easier to identify relationships between terms. Simplified representation. Instead of using long, complex expression, K-maps provide a compact way to express Boolean functions. Directly maps to logic gates. The resulting simplified expressions readily translate into a circuit diagram with logic gates. Coming to the advantages of using K-map. Using K-map simplifies Boolean expressions, which leads to more efficient logic circuit implementation. This can lead to reduced cost and improved performance. First one, easier to understand. The visual representation is more understandable than traditional algebraic manipulation. Second one, more efficient. The simplification process is often faster and more accurate using algebraic methods. Third one, less prone to errors. The structure of K-maps helps to minimize mistakes compared to manual manipulation of Boolean expressions. And fourth one is the systematic approach. The K-map provides a structured and systematic way to identify and combine terms. Coming to the disadvantages of K-map, while K-maps are incredibly useful, they have limitations, especially when dealing with large numbers of input variables. As the number of variables increases, the size and complexity of K-map also increases. The first one is limited scalability. For functions with many variables, more than 4 or 5, K-maps become too complex and difficult to use. Potential for errors. While systematic, large maps can be more prone to errors if the user isn't meticulous in grouping and identifying terms. Inflexibility for multi-level circuits. K-maps are less efficient when dealing with circuits that have multiple levels of logic gates. Constructing a K-map. Constructing a K-map involves creating a grid where each cell represents a unique combination of input variables. The number of cells in the map depends on the number of input variables. The first one is identifying input variables. Determine the variables that influence the function's output. Second one, determine the number of cells. The number of cells is 2 to the power of n, where n is the number of variables. Third one, label the rows and columns. Each row and column represents a different value combination of the input variables. Fourth one, fill the cells. Enter the output value, that is 0 or 1, for each corresponding input combination. Simplifying Boolean expression using K-map. Once a K-map is constructed, you can simplify Boolean expressions by grouping adjacent cells containing ones. These groups represent terms that can be combined. First one is identify adjacency. Group adjacent cells containing ones following the rules of K-map adjacency. Group size. The larger the group, the more terms are combined, resulting in a simpler expression. Write the simplified expression. From the groups, write the simplified Boolean expression by identifying the variables that remain constant in each group. Handling don't care conditions in K-map. Don't care conditions occur in Boolean functions when certain input combinations are irrelevant to the output. You can use these conditions to your advantages in K-map simplification. First one is to identify don't care combinations. Second one is to mark cells with X. Third one, include X in groups if beneficial. Fourth one, write the simplified expression. Coming to the applications of K-map. K-maps are widely used in digital logic design, specifically for minimizing Boolean expressions and implementing logic circuits efficiently. They are a versatile tool with application in various fields: digital logic design, optimizing logic circuits, reducing gate count, and simplifying circuit design; microprocessor design, implementing control logic, optimizing data processing, and reducing chip complexity; network design, designing network protocols, simplifying routing logic, and optimizing network performance. Coming to the robotics and automation, controlling robotic movements, implementing decision making logic, and simplifying control systems. Coming to the conclusions and key takeaways, Karnaugh-Maps provide a powerful method for simplifying Boolean expressions and optimizing logic circuit designs. This method enables efficient circuit implementation, reduces complexity, and enhances overall system performance. Coming to the simplified expression, K-maps efficiently reduce complex Boolean expression into simplified forms. Optimizing circuits, K-map leads to efficient logic circuit implementation, reducing components count and improving performance. And that's all about today's topic. Thank you.